All right, and welcome to our second lecture of Chem 120. And so today we're going to continue off of where we stopped at last week in chapter 1. And so what we're looking at this time is we're going to go a little bit farther about how we do our scientific measurements. And then we'll talk a little bit about density and some dimensional analysis as well. So last time when we stopped, we were talking about chemical reactions. And so we had talked about that you would have these reactants here. That's our starting material. And we would have our products that we're producing. And so this arrow in the middle was how we're going to separate that. That means that's where our chemical reaction is taking place. That's where it's transforming from those reactants to the products. The other part is that we're going to introduce a couple of these different symbols into how we start to communicate that language between our reactants and our products inside of these chemical reactions. So that arrow, we already know what that stands for. These letters here, they're standing for our elements, and we're going to talk about that in a little bit, and they can tell us basically the chemical formulas of those compounds. That's how many atoms of the element are present inside of that compound, and what elements are present. So in some ways, it's kind of like a recipe for each of the different chemicals. Outside of that, we're including what we call as the states of matter. So our states of matter have to deal with our physical states. So we have our three typical ones: gas, liquids, and solids. And so that G, like for our chlorine here, stands for gas. The S stands for solids, the L stands for liquids. Sometimes you even see the L is written like that. And they're just doing the same thing. Sometimes an L and an I can look similar. And so you might see that written in your books with the lowercase L that way. Now, why this matters is that the physical state of the material can give us some indications about what's going on. We can get physical transformations, which just the state of matter that's changing. And we had talked about this on last lecture, where we discussed whether we were seeing a physical change happening or a chemical change. And our physical changes, we wanted to know the name of all three of these states and the transitions that are going between them. This video is actually an example of a physical change that's occurring. What's going on is we have a liquid there, and that liquid's being held at a very specific temperature and pressure. And what we're going to start to see is there's going to be these changes that occur. So right there, that's the liquid freezing. It's turning into its solid form. Keeping it at the same pressure and temperature, this material is actually going to start to bubble right there. That's it's changing from its solid form to its gaseous form. That's what's creating the bubbles. And then it's refreezing there and turning back into the liquid. So it's kind of going through this cycle of its physical state changes. Every time you can see it kind of comes back to its beginning point. So the substance itself hasn't changed. That's why it's not a chemical reaction, but it is going through a system of these physical changes over and over and over again. Now, why that happens is because that material was put at a very specific point. It's called this triple point. At that point, all three phases of its physical states can exist at the same moment, the same conditions. And that's why we can see it both as a liquid, a gas, and a solid, and it's going through those cycles of changes. Typically, we only see one state at a time, unless we're at one of these transitions between them. And so that's why when you have a cup of water at room temperature, it just stays in its liquid form. When we heat it, we change its temperature, and it can then go up to its gaseous form, turn into steam. That's when you're boiling water, like for pasta. Or if you put it in the freezer, you can turn that liquid into an ice cube. But that's the change that are happening there. So those are our physical changes versus our chemical changes. Physical changes are used to separate mixtures. Chemical changes are used to separate our compounds into our elements. And so that's something about classifying matter that we want to jump back to. The other part that we have is what we call our extensive and our intensive properties. Now, an extensive property is something that when we measure it or we consider it, it depends on how much matter is there. So something like the mass, how much something weighs, changes based on if we have a lot of it or only a little bit. So if you have a piece of aluminum foil is just the element aluminum over and over and over again. Now, if we have a big piece of aluminum foil that has a large mass, right, it will weigh more. If we have a smaller piece, then its mass would change with it as well. So extensive properties depend on how much of that material is present, and so they change. So things like mass, length, volume are examples of that. Intensive properties, on the other hand, they don't change based on how much material you have present. So things like the density of it. So if you take that aluminum foil, whether you have a big piece or a small piece, if you take its mass and you divide it by its volume, it won't change no matter what size we have, right? Whether it's a small piece or a big piece. Things like the temperature of a piece of foil, that also doesn't change whether we have a little bit of it or a lot of it. They stay the same. Things like color. So those are examples of intensive properties. So extensive ones depend on how much material is present. Intensive ones do not. So if it doesn't change whether you have twice as much of it, it's going to be an intensive property. If it does change, it's going to be an extensive. Today, what we're going to be focusing a lot on is actually units. Now, units matter a lot. And an example about why that is we're going to talk about the Mars Climate Orbiter. So back in 1999, NASA was sending a spacecraft to Mars in order to measure the, to basically look at, do some studying on Mars, right? We were looking at the climate. Now, when this happened, what had been going on was there was this collaboration and people were developing code. And so two different people were working on this project. And so one of the engineers, when they were developing all their calculations and their programs, they were using one unit. And that one was going to be in this non-traditional one. It was called pounds per second. And that was to measure the force. The other person that was collaborating on it, they were using a different unit for the same thing. So there we're looking at newtons seconds instead of pound seconds to measure that force instead. Now, when they were working on it, neither one of them were putting in the units with that number as it was coming through. Instead, it was just coming through as a number. And so each of them were making the assumption that the other person was working in the same units as them. Now, what that meant was that when the spacecraft then went to Mars, when it was coming down into the planet, instead of releasing its parachute at the right time, it basically just destroyed itself instead because it was waiting for the number to get to one value before it would kind of do that next step. And the other one was never going to get to that right value because it was in a different kind of unit. So units matter. It's why when we take data inside of the lab, we shouldn't just write things like 3. Instead, we should have more information included there, right? Because if we just write down the 3, or if we have 3 centimeters, that's very different in our piece of information. Right? And so we want to make sure that we're including all of those units as we're writing those down. Now, for our course, the primary units that we're going to use, they're going to be called the SI units. Now, those SI units, a lot of their background is in the metric system, so we're going to talk a little bit about what those are. And so our base units are going to be shown here over on the left-hand side. So our base units are things like mass is going to be in grams instead of pounds, which we might be more familiar with. Length is going to be in meters instead of things like feet, inches, and yards. Time is going to be in seconds. Temperatures in degrees Celsius, or in another term, Kelvin, which we're going to talk about in a little bit. The amount of material, we can talk about that in terms of moles. And then the volume can be in liters or cubic centimeters. Both of those will work as well. And so the mass of an object is telling us how much material there is. That's what mass is measuring. It's how much stuff there is there. It's not just it's not the same as weight. Weight has to deal with the gravitational pull, so what's pulling down on it. And so for us, if you want to lose a lot of weight, one of the best ways to do that is become an astronaut, get sent into outer space. As soon as you leave the Earth's gravitational pull, you will lose a lot of weight very, very quickly. Mass is different. Mass is about the amount of material that's there. So when you lose your weight, you're not necessarily losing mass when you go into outer space. Your mass is going to be the same. Your mass stays consistent. So your mass is the same whether you are on Earth or on the moon, even though your weight is not the same. So mass is about how much material there is. A kilogram is another common unit for mass. It's about 2.2 pounds. And a gram is 1/1000th of a kilogram. So you can kind of see as we get through this why we start to use our metric system is that they have all of these different units that are easily related to each other. You don't have to memorize a whole bunch of conversions in the way you have to do with the imperial system, like 12 inches is 1 foot, but 12 ounces is not 1 pound, right? Those things do not align. For measuring lengths or distances, we're going to be using meters, or in most of the time in the lab, we'll be using centimeters. So the meter is slightly longer than a yard. Now, at some point, how they measured a meter was that it was supposed to be a 1/10,000,000th of the distance from the equator to the North Pole. And at one point, they actually just had a stick. They had a rod. That was how they kept the standard of what a meter is. Since then, they've come up with a better way to develop a meter stick. And so what they do now is it's the amount of time or the distance that a certain wavelength of light can travel in an amount of time. Right? So now that's more standardized, and then we can create much more uniform meters across the world instead of having to bring them all back to measure them against a rod over at the International Bureau of Weights and Measures. Right? Now, that's not the case for all of these properties. So things like the kilogram actually are still based off of a physical object. You still have to bring all of your masses to get weighed and massed against each other, which is the standard, the universal kilogram, in order to get the most precise readings. So we are trying to slowly move away from that. And so some scientists are working to find out a physical property that they can use to measure a kilogram. And that's what they did with a meter. And so that's how they're able to do it with a wavelength of light. Temperature, on the other hand, temperature we think of as a lot of times as being heat. And we do consider like the hotness and coldness of an object. But what it's really talking about is it has to deal with the amount of kinetic energy inside the atoms and molecules that are there for that matter. So we can tell this change in energy based on the flow of that heat from hot objects to cold objects. But it's really measuring how quickly those particles, whether those are atoms or molecules, are moving around inside that material that you're measuring the temperature of. This becomes important later on when we kind of get into the theory of it, but just know that your temperature is always related to this amount of energy. The hotter it is, the more kinetic energy it has. The colder it is, the less. Now, heat flows spontaneously from a high temperature to a low temperature, which is why whenever you have something hot and you place on something cool, the cool thing will heat up and the hot thing will become cooler. There's kind of 3 scales to measure temperature. We have Fahrenheit, Celsius, and Kelvin. Now, in the United States, we primarily use Fahrenheit. But for our class, we're going to be using our Celsius and we're going to be using our Kelvin. Now, the reason why is that while Fahrenheit's freezing point of water is 32 degrees and its boiling point is somewhere up there at like 270, it doesn't really align well with what we have going, water boils at 212 for Fahrenheit. it doesn't really align well with any values, right? So Fahrenheit was developed by one scientist. Instead, one way to do it is to use the Celsius scale, which boils water at 100 degrees Celsius and then freezes at 0 degrees Celsius. A lot easier, a lot simpler for us to see and to measure. But there was a problem with that. We start to get these negative values for temperatures, which sometimes inside of our equations doesn't actually make sense. And so they developed a third scale called Kelvin. Now, Kelvin's scale is what we will primarily use, but Celsius is easily interchanged in there as well. What's nice about Kelvin is it has this concept of absolute zero. So absolute zero is the coldest possible temperature that you could have. Absolute zero means that you have no kinetic energy. Now, since you can't have negative kinetic energy, then absolute zero is going to be the coldest possible temperature you can ever arrive at. Now, it hasn't been possible for us to get down to absolute zero, because if we were to get down to absolute zero, those particles would no longer be moving at all. And so that's a theoretical limit of where things should be. At that temperature, molecular motion would virtually stop since it has no more kinetic energy. Now, the reason why Celsius and Kelvin are commonly used is that Celsius, while it has those nice values, 0 degrees Celsius and 100 degrees Celsius, the scale between 0 degrees and 1 degree Celsius, so from 0 to 1 degree Celsius, would be a change of 1 degree Celsius. To go from 1 Kelvin to 2 Kelvin, that change would be 1 Kelvin, and these values are actually the same. And that's because to convert from Kelvin to Celsius, all we have to do is add 273.15. Sorry, that's to go from Celsius to Kelvin. If we want to go from Kelvin to Celsius, then we have to subtract the 273.15. So what that looks like is that 300 Kelvin, if we heated that up to 350 Kelvin, would be the same as us taking that 300 minus 273.15, being 26.85 degrees Celsius, and it would have heated to 350 minus 273.15, 76.85 degrees Celsius. So the distance between them, those gaps, are the same. So if you change 1 degree Celsius, you also change 1 Kelvin. If you change 10 Kelvin, you change 10 degrees Celsius. And so that's why we sometimes use those interchangeably, is because it's so simple to move back and forth between them. On the other side, we almost never talk about Fahrenheit. And that's because to convert from Fahrenheit to Celsius and Fahrenheit to Kelvin is a much more advanced formula. It's not quite as easy. And that's because a change of 10 degrees Fahrenheit is not equal to 10 degrees Celsius. In fact, if we were to change 10 degrees Fahrenheit, it would be like 5.56 degrees Celsius. So it's not so simple for us to move back and forth between them. And so Fahrenheit doesn't get commonly referenced. Instead, we see a lot of Celsius, we see a lot of Kelvin. For our masses, the easiest way to measure a mass is just go ahead and put it on a balance. So these are like the ones at the back of the classroom. We put it on there and we can see how much material there is. Now, mass is not normally created or destroyed inside of a chemical reaction. And so we should be able to consistently recover our mass from our reactants to our products. It lets us know that we haven't lost any material there. Volume on the other hand, is the amount of space an object takes up. And so the volume can vary if it's a gas, but solids and liquids have a constant volume. So for all of these liquids, when we pour them from one container to the next, their volume will stay the same. And this is why we can measure our volume of a liquid by pouring it in something like a graduated cylinder. We can take it from one container, we can pour it in another one that has the markings on it, and we can measure the volume or the space that it occupies. Solids can be a little bit trickier because they won't take on that shape of that graduated cylinder. And so for solids, sometimes we find it easier to find its volume by calculating it. And so we can find its volume by saying, oh, it looks very similar to something like a rectangular box, a cylinder, or a sphere. And we find its volume that way. And so that's one of the things that you're doing in experiment number 1 is you're looking at a milk carton and you're calculating its volume by saying it looks very similar to a rectangular box, something like this. So to find the volume of a rectangular box, we take its length times its width times its height. Now, you do not have to memorize these formulas. If you need them, I will provide them. But it is a good one to know for our rectangular prisms, our cylinders. So volume of a cylinder is the area of the circle. The area of the circle is pi r squared times its height, which is our h. So you can think of this as volume is equal to pi r squared times h. Now, while I would provide you with these formulas, it is important that you understand the terms of them. So you do need to know what the h stands for. You do need to know what the r stands for, or the diameter, right? So that way you do want to be familiar with those things. Spheres are our next ones. Spheres are a little bit complicated. They find their volume by using this one here, 4/3 pi r cubed. And so we want to make sure that we feel comfortable finding the volume of some of those objects. A last one can be the volume of a triangle, which is 1/2 our base times our height. And so we have that as well. So I just want you to make sure that you feel comfortable finding the volume of some of these objects. Even though you don't have to memorize the formulas, you just want to make sure that you feel you can understand how to use those formulas once they're provided to you. Now, what you'll notice with them is that when we started to use them, our units for our starting parts changed over our conversion into volume. We started with centimeters, and it ended up being cubic centimeters inside of our units. And that's because our units behave like our numbers. They do what our numbers do. So if they get multiplied together, then you add those, or you multiply those units together. So centimeters cubed. Volume of a cylinder. We had pi r squared, so that became our centimeters of our r. We squared that, so that became centimeters cubed. Then we multiply that by more centimeters, and so we get our answer in cubic centimeters again. Same thing for our volume of our sphere. So when you look at these things, volume, because it's talking about three-dimensional space, a common unit for that is always going to be some length cubed. That could be cubic meters, that could be cubic centimeters, but it ends up with that version. On the other side, area is a two-dimensional space that gets taken up, and so often you end up with things like square feet. Centimeters squared, right? Square yards, or square meters. So that's the difference between them. Areas are almost always going to be squared values because they're a two-dimensional space, whereas volumes are going to be cubed value units because they're a three-dimensional space. Now that we have all of our units, the next big topic that we're going to get into is something called density. Now, density was one of those intensive properties. It doesn't change whether we have a lot of material or only a little bit of it. It stays constant. It's consistent. This density relationship is very important because it's giving us a ratio. It's looking at the amount of material that's present, and then it's looking at the amount of space that that takes up. So our units for density show that relationship. It's grams per cubic centimeters in terms of solids, grams per milliliters in terms of liquids, but you can get a variety of those units. Density just always has that mass divided by that volume. So a small gold coin has the same density as a large gold coin. Those things stay the same because they are the same material, gold, and it's an intensive property of that gold. And so that's one way that people identify metals, is by finding its density. And if it's pure, or if it's all that pure metal, they can get an idea about which metal it is. So one way that you might feel comfortable with density is what we call the density triangle. The density triangle looks like this. We have our mass over our volume. And what you do is, if you want to look for something, you can cover up what you're looking for, and it gives you the relationship between the others. So if we want to look for our density here, I'm going to cover up our density. And you can see that our other part is going to be the mass here divided by the volume. And so that's our equation for our density. On the other hand, if we are looking for our volume, we could cover up our volume. And to find volume, we could see this as being our mass divided by our density. The last way to do that is if we wanted to look for our mass. So if we want to look for our mass, we cover that one up, and we then get this density times our volume to find our mass. And so a density triangle helps us see those relationships between all of them without having to memorize all those formulas at the bottom. Now, this can be a handy tool as you're first starting off with density, but it requires you to remember a lot of things in order for this to work. You might not have to memorize all three of those equations at the bottom, but you do have to memorize how to draw the triangle. On the other hand, if we then change from density to something else, we would have to memorize a new triangle for that with new relationships. Instead, what we can do is something that's called dimensional analysis. And this is probably one of the more important concepts from this course. It's definitely in the top 5. What dimensional analysis does is it tells you, why don't we just keep track of our units? We just need to keep track of the units, and when we work and do our equations correctly, when we end up with the correct unit at the end, we can make sure that we've done all of the correct steps along the way. So it's about using your units to help see the relationships between them. By changing our units over and over and over again, we can move them back and forth between them. So we'll do an example of this. Copper has a density of 8.96 grams per cubic centimeter. What is the volume of a bar that is in 440 grams? So we could draw out our triangle. We have our density, our mass, and our volume. We could say we want to look for the volume. So our volume should be our mass divided by our density. So our volume is going to be 440 grams, which is our mass, divided by 8.96 grams per cubic centimeter. When we divide that, we get a volume of 49.107 cubic centimeters. And we know that it's in cubic centimeters because our grams would have canceled, and we have that unit left over. And if we think about our significant figures, we have 2 significant figures in 440 because that 0 is not significant. It's a trading 0 with no decimal point. We have 3 from our density, and so our answer should be 49 cubic centimeters. So that's one way to solve this problem. Using dimensional analysis, what we can do is we can say, okay, we have density, which is 8.96 grams per cubic centimeter. We have mass, which is 440 grams. And what we want to find out is a volume. Now, the units for volume is going to be our cubic centimeters. So how can we arrange these two values in such a way so that we get those cubic centimeters left over for us, those units. So how can we put those pieces together? So one way to do that is we could say, well, this density one, we clearly have to have that centimeters cubed on top because we want that unit left over. So that gives us the 8.96 grams on the bottom. And if we want to get rid of those 8.96 grams, well, we should multiply that by the mass of our bar, 440. So if we look at this, we can see that the units of our grams, we have one here and one here. Those units are going to cancel out because we are taking grams and we're dividing by grams. So those units go away. Grams are gone. Grams are gone. And so our answer is going to be left over with just these cubic centimeters. So I just need to take whatever's on the top, 440, multiply that by 1, still 440, divide that by 8.96, and we're going to end up at 49.107 cubic centimeters, back to our 49 cubic centimeters, once we take our significant figures into account. So both of those ways work, and you can do either one, whatever you feel most comfortable with. But what I would encourage you to do is to start practicing this dimensional analysis. Dimensional analysis will be useful throughout this course. The density triangle will stop being useful once we move on past density, because then you're only learning it for just density, right? So density triangle is kind of like a temporary stopgap. It's only going to help you out for probably like the next week or so. And then later on, density does come up occasionally, and so you will need it then. But it's not going to be a long-term solution the way that dimensional analysis can really help you out. So a bar of gold has a length of 15 centimeters, a width of 8 centimeters, and a height of 6 centimeters. If gold has a density of 19.32 grams per cubic centimeters, what is the mass of the bar of gold? So we got a lot going on there. And so we can think about this in a couple ways. I'm going to take an approach where I'm going to look at it from our unit side. So take a moment, pause this video, go ahead and solve yours, and let's see how we do. So on the unit side, what that means is I'm going to look at my units and how I can get those to align. So I know that the mass of the bar of gold, looking at my reading through here, my mass should be measured in something called grams. That's how we're doing it for our density. So I'm looking to get to the units grams at the end. That tells me that my density needs to be grams per cubic centimeter. And so that means I need to get rid of those centimeters 3 times. So that means I need to have a centimeter on top, another centimeter on top, and another centimeter on top. Once I have 3 centimeters on top, it's going to take out all of those units down at the bottom. Now, I could have written this out in a couple ways. I could write it out kind of like how I did it here, where I have my volume first, where I multiply those 3's together, I get my cubic centimeters. I then multiply that by my density in order to get my grams per bar. But for me, I find this method a little bit easier to use as I lay out my boxes. Right? I can still find my volume in that way. It's my 15 centimeters times my 8 centimeters times my 6 centimeters. I can put my density in there, 19.32 grams, and my volume down at the bottom of it. And so what I like about this box system is I feel like it keeps my work a little bit neater. It makes it a little bit easier for me to go through and cancel out all of my units there. So my centimeters cancel with 1, my centimeters cancel with the second, my centimeters cancel with the third, so now my centimeters are all gone. I'm just left with my grams. And so how you do this is once you've set up your equation, when you're ready to start solving, you basically multiply everything that's on top and then divide by whatever's on the bottom. This is handy if you have to do a whole series of conversions, right? So if we're changing many different things over and over again, then you can work through that. You don't have to keep doing it on your calculator where if you make an error, it will go away. Instead, you can kind of line up your whole equation, get everything sorted out, and then do the math at the end. So it's one way to kind of keep your math organized and also to separate your math from all of your problem solving. But in either case, the answer that we're going to come to, once we look at our significant figures, which will only have 3, is going to be 13,900 grams. We'll do one more example of this. This is where density can come in handy, is to help us identify things. So in this case, what's going on is we have a can of whipped cream, and it weighs 475 grams. It has a radius of 3.62 centimeters and a height of 10.0 centimeters. If the density of a full can of whipped cream is 2.5 grams and an empty can is 1.16, is our can empty or full? Now, I also gave you here how to find the volume of a cylinder. 3.14 is where our pi is. So you can go ahead and try to answer this question. Is it empty or is it full? So to do this, one of the first things I did was I just went ahead and I found my volume. Once I knew my volume, I could then use its mass and its volume to determine its density. So I found its volume, 411 cubic centimeters. I found our mass, I took our mass from the question, 475, and I found its new density, that 1.16 grams per cubic centimeter. Now, when I look at that, our density is much closer to empty than it was towards full. And so our whipped cream is going to be an empty can. So now I know I got to go out and buy some more. On the other hand, if I had gotten a density that was closer to 2.5, I would know that it's a full can and I wouldn't have to worry. And if I ended up somewhere in between, then I would know that my can could be like 50% full, 25% full. And so this can be the helpful part about density, is we can use it to help do some identifications. Now, density is also related to some of those things like buoyancy. And so we can kind of think about if our density is higher than water, we typically will sink unless we're somehow trapping air, but that gets into a whole nother thing we're not going to worry about. And if we are lighter or less dense than water, then we normally float up on top. And so in here, I've gone ahead and I've given you these different densities. And so let's try to classify them. Do you think they're going to float or do you think they're going to sink? Now I've gone ahead and I fixed the formatting on it. So now the units are better aligned. And so we want to think about whether you think they're going to float or if they're going to sink. So density of water is 1.00 grams per cubic centimeter. It's actually one of the nice parts about water. It's got a very simple density, easy to remember. So styrofoam is going to sink. Styrofoam is less than water, and so it's going to float. So all the ones that float, I'm going to circle with that orange. Aluminum, 2.7 grams per cubic centimeter, definitely a higher density than water, so it's going to sink. Gasoline, 0.72, lower than water, so it's going to float. Copper, higher than water, it's going to sink. Gold, much higher than water, it's going to sink. Olive oil, much higher than water, it's going to float. And so that's a little bit about density. Now, I'm including a video here that talks a little bit about displacement, which is kind of a fun thing to do. I like this guy. He's a great resource for some additional chemistry help. He does a lot more on the conceptual side of things. And so I'm going to include this inside the lecture page. So if you want to, you can always watch his videos as well if you need some extra resources. But he's going to talk a little bit about a concept called displacement. You do want to understand displacement. It is one of the ways that we measure the volume of an object, especially something that's irregular. Now, dimensional analysis, we've seen how it can be used, but the big part of dimensional analysis is that it utilizes something called a conversion factor. Now, a conversion factor is kind of the basis of dimensional analysis because it is letting me know how much of one unit is equal to another. So it's a ratio. We can show that 1 inch is 2.54 centimeters or 2.54 centimeters is equal to 1 inch. And it's how we convert from one unit to another. That's how it gets its conversion factor. You probably do this all the time. You just might not have known it, right? We use them often in word problems where you might think of something like the price of 1 pound of red peppers is $1.39. Now that tells you that 1 pound of red peppers will cost you $1.39. So if you wanted to think about how much money that would be, you could say that as 1 pound for $1.39. So you could say if I had 2 pounds of peppers, you could use that conversion to figure out how much money you need. On the other side, if you then had $5 and you wanted to buy as many red peppers as you could use this conversion factor to convert that money into red peppers. Now we see this if you've gone to the gas station and it has a gallon of gas is $2.25, or right now it's probably like $2.97. You can use that to convert. So if you only have $20, you can get an idea about how many gallons of gas that's going to be. You might even use it in miles per gallon, right? You might think about, well, I have I've driven 250 miles since the last time I filled my tank. How many gallons of gas do I need? So conversions factors are something that we use all the time and we might not even know. A common example of that is 12 inches to 1 foot. You've probably done that conversion many, many times without realizing that they were fractions as you're looking at them. Now, to help with this, if you feel like your conversions are a hard part, if that math about turning them into fractions is confusing, I want you to look at these extra resources that I've linked below this video. We're going to do something called conversion dominoes. We're going to take our dominoes and we're going to try to practice using them to help us convert from one thing to another. So in this case, if you've ever played dominoes, what you need to know is that your starting point has to match the next tile that you lay down. So for me to go from this 3, I need another tile that has that 3 on it. For me to go from that 6 of that tile, I need to lay down another tile that has a 6 on it. So if we wanted to go from this 3 to that 5, I would have to lay down tiles where the beginnings match the one from before. The 2's match and the 5's match. Conversion factors are the same way. For us to go from one unit to another, we can do a whole series of tiles. That part doesn't matter, as long as each tile that we use, the beginning units match the next, match the end units of the one that came before it. So miles to miles, feet to feet, yard to yard. Once we have that, we can go through and we can practice doing all of those different conversions by treating these dominoes like they are fractions. So that miles to feet, we just need to flip it over so that way we started with miles and the next time we saw miles, it was down at the bottom. Feet go on top, feet then come down at the bottom. And so the idea behind it is that if you have the number 6 and you multiply that by 1/6, those 6's basically cancel out in some ways. You end up with 6 divided by 6, which is really 1. And so you can think of them as going away. So a miles that's on top, in this case that we start with, when it meets a miles that's on bottom, it's like our 6 dividing our 6. It's going to turn into 1 and it's going to go away. And so our units behave in the same way. If they're not on the top and the bottom, if instead we had a 6 over a 1, then instead what we see is 6 times 6, which is our 6 squared. And so our units behave the same way. So if they're not lined up correctly, what you're going to see is something like miles. And then the next time we see it, we might have flipped it the wrong way. We had miles over feet. And so instead of canceling out, we would get these weird units of miles squared over feet. Not very helpful. And so you want to pay attention to that as you line up your problems correctly. So you want to work through that worksheet with our dimensional dominoes, and they have you practice some of these. We start off first with just dominoes, Then we move on to just the units, and then eventually we'll do units with numbers. And so you want to work your way through it. This is normally something that we would do in class together, but as we don't meet in class together, then you want to do that. I've also included on there a list of the specific tiles that you can use. So they're going to have the conversions for your different units, but they'll also have you practice with just the conversions or only specific numbers for our starting dominoes, the ones with just numbers on them. Once you feel comfortable with those dimensional analysis problems, you can come back and we are going to continue on a little bit more. So this is a way that you can kind of think of when you try to set up a conversion problem, is you try to think of what units you have as you're going through that word problem. List out, oh, I start with centimeters cubed. I start with grams. Think of what you want. You might want to end up with our density, which is going to be grams per milliliter. And then think about, well, how can we do that? What conversion factors could we start with? Maybe we know that 1 centimeters cubed is 1 milliliter. Maybe we know that 1,000 1 liter is 1,000 milliliters. It all depends on what you're working with, where you're trying to go from. And so then when you want to connect that chain, we could have started with something like, well, our grams should go on top. We should divide that by our cubic centimeters because we want that at the bottom. And we want 1 cubic centimeter and our milliliter to cancel out, and we could get into grams per milliliter. And so you can practice laying out your problem, setting up those conversions. This is something I would strongly recommend if, as you start going through the homework problems, what you realize is you're often making the mistake when you're multiplying by things when you should be dividing, or dividing when you should be multiplying. A lot of that can be solved if you pay attention to your units. If your units don't cancel out correctly, it's why you're ending up with the wrong answers. Now, we talked about one of the strong points of the metric system is prefixes. And so these are going to be the 8 prefixes that I expect you to know and memorize for our class. We should be able to know what the prefix means, so its name, the symbol that it uses it to stand in, and how much that value is for. Now, the reason why these are so important, or these are kind of like our most common ones, and these prefixes can be used for any unit. So we might have heard of a kilometer or a kilogram. Right? Both of those are the same prefix modifying something that came before them. So the base unit is a meter, and now we're doing kilo. So kilo stands for 1,000. So 1 kilometer is 1,000 meters. In the same way that 1 kilogram is 1,000 grams. That also works for things like milli and nano. And so things like kilobytes, 1 kilobyte is 1,000 bytes. And a megabyte is 1,000 or 1,000,000 bytes. So we do use these prefixes all the time as we modify our different units. And so we want to be familiar and comfortable with those. And so these are the 8 common ones that we do want to pay attention to. The other one is you want to make sure that you clearly identify whether it's a lowercase or an uppercase, because some of them will be very similar. This is millimeters. This is megameters. Right? Those two things have a very, very big difference in their values. A millimeter is smaller than a meter by a lot, 1,000 times smaller. A megameter is 1,000,000 times bigger. So you want to make sure that you're clarifying which one's lowercase, which one's uppercase. The rest of this slide pack is just some practice problems for you to work through how to practice converting some of those units as we move back and forth between them. And so you do want to work your way through there. practice them. So when the slide comes up with the conversion, take a moment, work your way through it, and then we do have the answer that's going to come up after that. So in this case, we're going to convert the weight of a 10-pound block of wood into kilograms. So 1 kilogram is 2.20462 pounds. So a 10-pound block of wood, I should start with that 10 pounds. I multiply it by the conversion factor of 1 kilogram per 2.24062 pounds. I get my answer here, and then I want one significant figure, so I end up with 5 kilograms. If I was writing that out, it would have looked something like this with my 1 kilogram, 2.20462 pounds. And so this would have been my 4.5359 kilograms. Now, what you'll notice is that one of them is generally going to be exact compared to the other, right? So most of the conversion factors, you can imagine that the one that's the 1 is an exact value for it. And all of the other uncertainty lies in that second number, right? So they're trying to say that for exactly 1 kilogram, it's 2.20462 pounds, right? And so just keep that in mind when you're looking at your significant figures. We're taking a trip to Europe, and all the speed limits are marked in kilometers per hour instead of miles per hour. We're driving 90 kilometers per hour. What do you think your speed is in miles per hour? So for this one, our units, we started off with kilometers per hour, and we want to end up in miles per hour. So I want to get rid of that kilometer. So I'm going to put my kilometer down, and I know that conversion into miles. So 1 mile is 1.609 kilometers. I then just need to add in my 90.0, and I can find my answer. And so it should be 55.9 miles per hour. Now this one gets a little bit harder. In this case, we know that each aluminum can weigh about 25 grams. If we're trying to create a block of aluminum that has a volume of 2 liters, how many cans will we need to melt down? And then aluminum has this density. So there's kind of a lot going on here. So we might need to organize. What we're looking for is cans. This is going to be what our answer should be in. What we're starting off is we know that we have 2.00 liters of our material. From there, we have a lot of different conversion factors. So we know that 1 can is 25 grams. We also know that 2.7 grams is 1 milliliter. And we know that 1 liter is 1,000 milliliters. So if I want to set this up, I might start with my liters. From those liters, I could change them into milliliters. From those milliliters, I could change them into grams. And from those grams, I can change them into cans, which is what I'm looking for. Now, if you didn't try this before you saw the answer, what I would say about conversion factors is it's always easy when someone else lays down the pathway. When you see it laid out, it's like, oh, that makes sense. Sometimes the hardest part of the problem is laying out that pathway. So you want to make sure that you're taking that time, you're taking the time to pause the questions so you can practice going through and laying out your problems before you see the solution. It's going to help you out the most for when you're trying to practice your exam and your quiz, because when those come up, there's not going to be someone that shows you the pathway before you start. So we have our 2.00 liters. We have 1,000 milliliters is 1 liter. We have 2.7 grams is 1 milliliter. And we have 1 can is 25 grams. We can work through all of that. And we will find out that we need 220 cans. So we need to melt down 220 cans, and we should end up with enough. And so that's kind of what you need to do with that. And this one we already did. So we're all set. So practice your conversions. There are different types of conversion problems. Some of them will be word problems. Some of them can be very straightforward like this. This one is really having you practice through your prefixes. So try to identify what prefixes you have. What does this K stand for? What does this G stand for? And then you can practice making those adjustments for the next one. So example 1, we went from those meters to our kilometers, our kilograms to our grams, our Kelvin to our gigakelvins, centimeters to megameters, and milligrams to nanograms. All right. Practice on those. Conversions are going to be a big topic moving forward in the future. So keep on practicing with that. We'll be working with them a lot more next week as well. Good luck.